ladies and gentlemen, boys and girls. My name is Mr. Do, and science is my business. You are welcome to Mr. Do Scienceworld. And today we're going to look at the law of conservation of momentum. Alright, so we're looking at the law of conservation of momentum. So let's straight away go into the concept itself. And then after the concept, we'll be doing with some calculations. And then when we do with the calculations, after the law of conservation of momentum, we'll be looking as well at what? Elastic and inelastic collusion. Alright, so let's begin with the concept. So now let's look at the law itself, the law of conservation of momentum. The law of conservation of momentum can be stated as follows. And for a collusion occurring between object A and object B in an isolated system, the total momentum of the two objects before the collusion is equal to the total momentum of the two objects after the collusion. That is, the momentum lost by object 1 is equal to the momentum gained by the object 2. So we can state or reframe the law to say that the total momentum of a collection of objects or a system is conserved. That is, the total amount of momentum is what? Is constant or unchanged in value. Not just in value, but both in value and what? In magnitude. So thus, if two or more bodies interact, the total momentum before interaction will be equal to the total momentum after the interaction. And then we can look at this mathematically to say that, the momentum at the initial stage will be equal to the momentum at the what? At the final stage. Which simply implies, like we can say that the sum of the what? Initial momentum is equals to the sum of what? The final momentum. So this sign here is what? Referring to what? The summation. That is the sum. So the sum of the initial momentum, because remember we are talking about what? Two objects here, which means that I am having object 1, okay, and in object 1 its momentum is going to be what? M1 V1, right? If it is the initial stage, then it's going to be what? M1I plus M1I times what? V1I, which is the initial momentum of what? Of the object 1. Then if you are looking at the object 2, we are also going to have what? The initial momentum. So let me call here initial momentum of the object 2. Let me call here 2I. Okay, all right. And then, sorry, 1I here. And then have this one to be 2I. So that this one is going to be what? M2I multiplied by what? V2I. So the initial momentum of the object 2 and then initial momentum of object 1. Okay, the sum of these two must be equal to the sum of the what? Of the momentum of these two objects at the final stage. That means that we are going to say that, okay, P final of 1, okay, is now going to be P final of 1 is now going to be M what? Final of 1 V final of 1. And here we're going to have 2 P2 final, which is also going to be what? M2 final multiplied by what? V2 final. And if I add the sum of this, the law is saying if we add the sum of these what? Momentums, it must be equal to the sum of these two momentums. So that is what the law is trying to tell us. So in other words, I am going to write this one together as I have stated it there. So let's check it and see. That means, what are we going to say? We are just simply saying that M1I V1I plus M2I multiplied by V2I is equals to M1 final, okay, V1 final plus M2 final multiplied by V2 final. And that is the law of conservation of momentum. Alright, now let's look at something here. One thing to remember about this is that we have said earlier that momentum is what? Is a vector quantity. So if momentum is a vector quantity, then so the direction of the vector is important. So whenever you are dealing with a calculation under momentum, we need to consider the what? The direction. Because the direction of the motion is important, because it is what? It is a vector quantity. Let's try and apply this law right now. So we're going to apply the law by first looking at some calculations here. So let's look at some calculation, some questions from here. What is the question saying? Okay, right. So let's look at the first question. A boy of mass 45 kg running at a speed of 3 meters per second jumps onto his what? Stationary skateboard of mass 0.8 kilograms. The question is saying calculate the speed at which the skateboard and the boy move off immediately after the boy gets onto it. Alright, so let's look at the information that we were given according to the question. The mass of the boy is given to be 45 kg. The initial velocity of the boy, which is VB initial, is given to be 3 meters per second. Then the mass of the skateboard is given to be 0.8 kg. The initial velocity of the skateboard. Now the skateboard was at stationary position before the boy jumped on the skateboard. So therefore, the initial velocity of the skateboard is what? Is 0. So that is going to be 0 meters per second. Now let's check. Immediately the boy jumped on the skateboard, the boy and the skateboard move together as one what? Component. So because they are moving together as one unit, they are going to have what? A common velocity. Which means that their final velocity is going to be common. And that is the one that we are going to look for. Right. So that is what we are looking for. Let's state the law of conservation of momentum. And then we are going to solve from there. The law of conservation of momentum says the initial momentum is equals to the what? The final momentum. So we can just simply say that MBI multiplied by VB, or MB multiplied by VBI plus MS multiplied by VSI must be equals to MB VBF plus MS VSF. And remember that these velocities is common because the two bodies now are moving together as a single unit. So if they are moving together as a single unit, they have a common what? Velocity. So this formula will become like this. And then we will multiply by this common velocity for that. And now let's do the substitution and solve for the V final that we are looking for. Alright, so if I do that, this is given as 45 multiplied by what? Multiplied by 3. And then plus the 0.8 multiplied by 0 is equals to 45 plus 0.8. And then I will multiply that by the V final. And what I want, remember this is going to resolve into 0. And what we are going to have is going to be just this and that. And if we multiply these two together, we are getting what? 45 multiplied by 3. And that is going to be what? 135. Okay, so we have 135. And that must be equals to 45.8 VF. And I just divide this 135 by 45.8, and what are we getting as our what? Our final velocity. All right, so the final velocity is now going to be what? It's going to be 2.9 what? 2.95. I'm leaving my answer in two decimal places, so that is 2.95 meters per second. I can decide to leave my answer in what? In the right sigfig. And if you're leaving our answer in the right sigfig, we are dividing, so we have to leave our answer in the lowest what? Decimal place. And here the decimal place here is what? It's nothing, so it should be a whole number. So therefore we should have it as what? 46 what? Meters per second. That is the right what? Sigfig. Right. Okay. Let's move on to look at the next question. Alright, so let's look at these two types of what? Collisions that we have. We're going to begin with the what? Elastic collision. A collision is said to be elastic if the kinetic energy is conserved. Most collisions are never truly elastic, and there is always a change in energy due to what? Energy transfer as heat, deformation of the objects, and the sound of the impact. However, if the objects do not deform very much, for example, two belloid balls or a glass marbles colliding, then the loss of initial kinetic energy is small enough to be ignored, and then the collision treated as what? Elastic. Too simple, you can think of any what? Collision where the object bounce off each other as what? Elastic collision. So like for example, you can see we can have three different scenarios where we are going to have what? The elastic collision. We are going to have what? Three different scenarios of what? Having what? The elastic collision. Let's look at these three different scenarios that we can have. Let's assume that I have these two markers, okay, and that is why I am having two different colors. Trying to demonstrate to you that you can see from here, these two markers now, they are all going to what? They are going to collide with one another. And let's see the situations that we can have. We have a situation where this is at stationary and this one now is what? Is moving. And you will see that they will move until they will collide, and after the collision, this stops and this continues to what? To move. That is one what? Possibility that we can have, right? There is another possibility that we can have where we can see having a head-on collision where these two markers, one is coming from this direction and the other is coming from this direction. They come, collide, and then they move backward, or they bounce backward again. They collide and then each of them what? Bounce backward. That is another scenario that we can have in terms of what? The elastic what? Collision. The last scenario is, let's assume that you are driving and another car is in front of you like this, and you were just moving, and maybe you just take off your eyes, and before you just see, you go and hit the other car behind. After hitting the trunk of the other car, the car does not stop, it keeps on moving, and your car is also what? Moving. So we can have such scenario as well, where there is a collision and the two are all moving what? In the same direction, but with what? Different velocities. So you can see that in this elastic collision, in each scenario or in each of the what? Of the cases, the two objects will move with different what? Velocities. They are not going to move with what? With a common velocity. So let's try and summarize what? Elastic collision and see exactly what we are talking about in terms of what? Elastic collision. So question number one, or the point number one that we can raise, is that in elastic collusion, there is no deformation of colliding objects that occurs. There is no deformation. The object does not deform after the what? After the collusion. 2, there is no change in the kinetic what? Energy of the what? Of the object. The kinetic energy is kept what? Constant. Kinetic energy is what? Conserved. So 3, kinetic energy is conserved. That is, the total kinetic energy before the collusion will be equal to the what? The total kinetic energy after the what? After the collusion. And the last point, which is point number 4, is that no other form of energy is produced. We are not going to produce any form of energy again. So there is no what? A transformation of what? Of energy. So no other form of energy is what? Is produced. Alright, let's look at the inelastic collusion. Alright, let's look at inelastic collusion. Inelastic collusion are one in which the total kinetic energy is different after the collusion. That is, kinetic energy is not conserved. Extreme examples of inelastic collusion are objects that sticks together after the collusion and then they move as one word, one unit afterwards. Like the calculation we did, where we saw that at the end of the day there was what? A common velocities that they were moving with. That becomes what? Inelastic. Alright, so let's look at that way. That is the situation where you can see that, okay, you are driving your car and then another car is at a stationary position and you just drive straight away and then collide with the stationary car, and after colliding with that stationary car you stick together and move together as one word system until a certain distance before you come to what? To a stop. That is what? Inelastic collusion. So let's look at, in summary, what are we saying in terms of inelastic collusion? What we are saying is that 1, colliding bodies deform after what? The collusion. So that means that one object deforms the other object. So you can see they will collide, and after the collusion, then you see a situation where there is what? A dent, maybe on the car, okay? Or you see that the other car gets stacked into the other and then they are moving together. So definitely there is what? A deformation. 2, it generates heat, which means that there's what? There's a transfer of energy in there. 3, remove kinetic energy from the system in other ways. That means that because there is heat, there is what? There's a loss of kinetic what? Energy. And 4, kinetic energy is not conserved. Kinetic energy is not conserved because there is a loss of kinetic energy, which kinetic energy has been transferred as what? As heat. They've been transferred into heat. So therefore, we are saying there is a loss of what? Kinetic energy, making the kinetic energy not to be what? Conserved. Alright, in all, what we will say is that momentum is conserved in any collusion between objects, but kinetic energy is only conserved in a perfectly elastic collusion. Take note of that, guys. What we are trying to tell you here is that in any type of collusion, what is expected is that we expect that momentum should be conserved. That means the total momentum before the collusion must be equal to the total momentum after the collusion. But in terms of kinetic energy, all collusions does not lead to what? The kinetic energy being what? Conserved. There will be some collusion in which kinetic energy will not be what? Conserved. And there will be other ones in which kinetic energy will be what? Conserved. Elastic collusion will lead to what? Kinetic energy being conserved. Inelastic collusion will lead to kinetic energy not being what? Conserved. Alright, let's forge ahead and then look at some problems here. So our first problem here, what's the first problem? The first problem is saying A granny who is 80 kg in mass swings around the ring with a velocity of 6 meters per second. She suddenly collides with Johnny, who is of mass 40 kg, who is at rest directly in her path. After then knock him off, she pick him up and then continue in motion without what? Without braking. Alright, so now Johnny, let's look at it. Granny is running a race and Johnny is just right on the path of Granny. Granny was going, instead of Granny to just collide with what? With Johnny, Granny decided to pick up what? Johnny, and then move together with what? With Johnny. So you can see that Granny and Johnny are now together. They are being considered as what? One unit. And if they are being considered as one unit, it means that they are going to move with what? A common velocity. Whatever velocity that Granny will be moving with after taking what? Johnny, is going to be the velocity of what? Of Johnny as well. So if you look at this type of a problem, let's see the question. It says, determine the velocity of Granny and John. Assume that no external forces act on the system so that it is an what? Isolated system. Isolated system. Let's understand that. What is an isolated system? An isolated system is any system without any external what? Forces. Where there is no external force interfering into the system, then we say the system is what? Isolated. So, first question is asking us to determine the velocity of Granny and what? And Johnny. And then the second question is saying, what kind of collusion is this? Alright, let's go straight in solving the problem. If we look at the question, we can see that here, Granny is having a mass. So the mass of Granny is now 80 kg. And the velocity with which Granny was moving with at the initial stage is 6 meters per second. And we were told that Johnny also has a mass of 40 kg. 40 kg. So Johnny is having a mass of 40 kg and Granny is 80 kg. What is the initial velocity of John? Alright, if you look at the initial velocity of John, John was at a stationary position because John was resting. Therefore, John is having 0 meters per second what? Velocity. And now we are told to find their common velocity after what? After collision. After Grandma has picked up John, we want to find the velocity that the two of them are going to move with. Alright, so let's go straight away in solving the problem. We need to state what? We need to state our what? The law of conservation of what? Momentum. And that is the sum of the initial momentum must be equals to the sum of the what? Of our final momentum. And if you look at this straight away, this means that it is mg vg is plus mj vj is equals to what? Mg plus mj multiplied by v final. And this is what we want to look for. First, let's take the direction of motion. And we are going to take to the right as what? As positive, or to the east. So if you are moving in the east direction, that is positive. Right, and if you look at the diagram that we are having there, you can see that Granny was moving in what? In an east direction. So if Granny is moving in the east direction, then let's do the substitution. So the mass of Granny is 80 multiplied by the velocity, which is 6, plus the John is 40 multiplied by 0, and that must be equals to what? 80 plus 40. And that will be multiplying by what? The V final. Alright, so we're going to deal with that. Let's take our calculator. And we say 80 multiplied by 6. And what are we getting? We're getting 480. So we have 480. And this is going to give us 0. So from here, this is going to give us 120. And we'll divide through by what? 120. And let's say 480 divided by 120. And what are we getting? Getting what? 4 meters per second. Alright. 4 meters per second, what? To the right. So we can see, or to the east. East. So we can see that after the what? After gravity picked up John, they are all moving in the what? In the east direction. Right. And let's see, we just the question, the next question is asking us about what type of what? Collusion that is going to be. Well, let's see, we have just said that it is only in inelastic collusion that after the object what? Collides together, they stick together and move as what? A common unit, having a common what? Velocity. Therefore, this problem is what? Is an inelastic what? Collusion. So inelastic collusion. So we are having it to be what? An inelastic collusion. Right. So what type of collusion it is? It is what? It is inelastic collusion. Let's forge ahead. The next question. And the next question is saying, in a collision seen below, which vehicle experiences the largest force? So we can see the collision is between a truck and a car. And we are asked this question. In the what? In the collision seen below, which vehicle experiences the large force or the larger force? A larger force. A says truck, B says the car, and C says what? Both the what? Both are the same, or both are experiencing the same forces. Well, the question says, using the principles of physics, explain your answer. Well, we are having a car and we are having a truck coming together and they are colliding together. To a layman point of view, straight away, the layman is going to tell you that the truck is going to have what? A larger force. But the truth of the matter is that the larger what? The truck is not going to have a larger force. Neither the car going to have what? A larger force. They are all going to have what? Equal forces. Their forces are going to be what? Equal. But the what? The magnitude of their forces are equal, but the direction of their forces is what is going to be different. And this is according to the what? The Newton's third law. Because the Newton's third law says that if an object A, okay, lean on an object B, the object B will also exert a force which is equal but opposite in what direction to the object what? A. That means that to every action there is equal and opposite what? Reaction force. So that is what the Newton's third law is telling us. So therefore, according to Newton's third law, the truck and the car, they are both going to have what? Equal forces. Alright, let's move on. Let's look at the next question. The next question is saying, why is it that the car and the car driver are always or almost always worse off as a result of this collusion? Explain your answer. Okay. If we look at the problem at hand here, the first one that we solved, we have said they are all having equal forces. But now the track is bigger. So, if the track is bigger, what you have to understand is that the track is going to have a larger mass, but what? A smaller velocity. Because it is very heavy, it has a greater mass, it will not be able to move what? Faster. So we can see that in our, if you try to find our momentum of the maybe the track, okay, it is just going to be like, you know, we are having what? A bigger mass, but what? A smaller what? Velocity, a smaller change in velocity. Or let me just use this. Okay, let me just use the velocity because I'm talking about momentum here. But on the car side, you can see the car is just going to be something like this, a smaller mass and what? And a bigger velocity. So that simply implies that the car is going to have a greater velocity. And if the car is having a greater velocity, what does that imply? That simply implies that the car is going to move what? At a faster rate, having what? A greater velocity, and that will make that car to become what? More what? Dangerous in terms of sustaining what? Injury. Because then you're moving at what? As a faster speed. Right. So if we look at this and we try to find the change in momentum from here, we can see that the change in momentum of this track will be equal to the what? The negative change in momentum of the what? Of the car. They are all going to be equal, but they are going to be what? Opposite in direction. So their momentum are equal because what? This is having a larger mass but a smaller velocity. This is having a smaller mass but a larger what? Velocity. So their change in momentum is going to be what? Is going to be equal, but what? But opposite. Alright, let's move to the next question. Alright, so let's look at the next question. And if you look at the next question, it says, if conditions are such that the car and the track end up at rest after the collision, how can we say that the momentum has not been lost for the system? So we're trying to look at this from this point. Now the car and then the track, they have collided, and after the collision they are all at a standstill, they are at rest. How can we say that there is what? No loss of what? Momentum in the system. How can we say momentum is still conserved from here? Alright, let's look at this. We can prove this mathematically. So let's try and see. Remember that according to this question, the mass of the track is given to us as 2,400. So let's see. From there, we are given that the mass of the track is 2,400 kg, and it was moving with what? An initial velocity of what? Of 10 meters per second. Now the car on the other hand is having the mass of what? Of 1,000 kg, and it's having what? Initial velocity of what? Of 24 meters per second. Right. Now the cars and the track came to rest after the collision, which means that the final velocity of the track is now 0, and the final velocity of the car is also what? 0, because they are all at what? At rest. So now let's go on and do our calculation for the momentum, and let's see. We said the initial momentum must be equal to the what? The final momentum. That is according to the what? The law of conservation of momentum. To say momentum is conserved, this is what we are saying. So let's see, what is this? This is MT/Vt plus MCVC. It's now equals to what? MT/VTF plus MCVCF. And now let's do the substitutions and see. We can see the mass is now 22,400, and we're going to multiply that by 10. Okay, now there is a head-on collision. So whatever that is going to the east or to the right, let me put it that way. Right is positive, and then I'm going to take left to be negative. Good. So now the velocity of this track is going to the right, so that is positive. On the other side, the car is having a mass of 1,000 kg, and I'm going to multiply that. Let me put this in brackets and make it look more beautiful. And this is now, the velocity is now moving in the left direction, so that must be what? Negative. So negative 24. And that must be equals to 2,400 multiplied by 0 plus 1000 multiplied by 0. Everything here will be 0. Now let's see. So the final velocity, the final momentum is now 0. Let's see if our initial momentum is going to be 0. Alright. So if we multiply this by this, we get 24000 plus, it becomes negative. Negative what? This is 24 and there are 3 zeros again. I bring 3 zeros. So let's see. This is 24,000. This is also 24,000. To 24,000 minus 24,000, what are we getting? That is going to give us what? 0. So we can say that the final momentum is 0 and the initial momentum is also what? 0. Because final momentum is 0 and initial momentum is 0, then we can conclude to say that what? Momentum is what? Is conserved. Thank you very much for watching this video, and please don't forget to subscribe to our YouTube channel. If you have not done so, please do subscribe by clicking on the what? On the red button there. And after subscribing, please click on the notification bell so that anytime we release any new video, you'll be the first person to watch it. As you subscribe, please share our videos to your friends. Let them watch it. Not only you need to learn, everybody needs to learn. So give it to your friends. Let them also learn as well. And as you are watching the video, please try and like our videos. Click on the like the videos for us. Give us comments so that we'll be able to improve on whatever that we are doing. Alright, thank you very much, and see you in the next time when we will be dealing with another version of momentum. Alright, so all that I will say to you is that keep learning, for learning is life and life is learning. See you next time, and bye-bye.